So the last thing we're going to do in Unit 1 is learn how to draw a graph. There will be a question on your test where you have to draw a graph, and it's going to be up to you whether you want to do it by hand or computer generated. So we are going to do this graph by hand and then again computer generated and see how the two do. So when we are drawing a graph, this is our data. This is always going to be our x-axis. This will always be our y-axis. So this is the effect of original speed on distance. Now, let's actually read the question so you know what I mean by that. Two physics students were measuring the distance it takes for a driver to bring a car to stop, depending on their original speed. They predicted there would be a linear relationship. So first off, we want to do this graph. Now, even though we need a title and our axes labeled and our scale, it doesn't matter what order we do these things in. So let's first off figure out what goes where. Original speed is what's going to go on my x-axis. And it's going to be measured in meters per second. And then this distance is actually a stopping distance. So I'm going to put stopping distance here. And it's measured in meters. Okay. Now, if I was going to do a title, I could do that now. It's the effect of the original speed on the stopping distance of a car. So actually, you know what? I'm going to keep typing. I type so much better than I print. The effect of original speed on stopping distance of a car. Okay, then let's figure out our axes. So for my x-axis, I have to go from 0 to 29 in how many grid lines? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I have to go 29 in 15 grid lines, which means 29 divided by 15 gives me 1.9. That means that my scale has to be at least every 1.9. So I'm going to choose every 2. So it's going to start at 0, and then my scale is going to be 2. And then you don't have to label every line. I'll go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and then this will go up to 30. My y-axis, I have to go up to 22 in how many grid lines? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Which means that it has to be at least 2, so let's just go 2. 2, 4, 6, 8, 10, 20, and I can label the top if I want. Okay, now let's plot our data points. So the first question I always ask is, can you put a point at 0, 0? Right? Can we go through the origin? If your original speed was 0 meters per second, would it take you 0 meters to stop? Yes. So let's put a point at 0, 0. When I'm graphing using a computer, I always like to put that in there just so that my line goes all the way through. I don't know if you notice on this guy up here, I guess I kind of pointed it out, but the line stopped there because the computer didn't know if you wanted it to go through 0, 0 or not. I find it just easier to tell the computer, just go through 0, 0, and it makes my life easier. And then we're going to plot our other points. So when our original speed is 11, our stopping distance was 8. What a 10? I can't even, there's no way I would read that as a 10. 2, 4, 6, 8, 10. Okay, so 11 would be halfway between 10 and 12, and then 8. And then we have 16 and 12. 2, 4, 6. 20 and 15. 2, 4. 25 and 18. And 29 and 22. Okay. Now the question is how to draw my line of best fit. Now I don't have a ruler, but I have this funky thing on my graph. If it'll let me do it, I have to start it here. Oh, it's not going to let me do it. Okay, let me see if I start it the other way. There we go. Okay, so I'm going to go through the origin. Ideally, I would have started. Oh, it's not going to let me do it. So it's really hard to make this happen using a computer. So ideally, you would hold a ruler up, and then you want to look to see that you can draw a line with sort of equal number of points above and below the line. I mean, the computer does it accurately. We can only do the best we can, but I don't think. Oh, there we go. It's letting me. Okay. So let's see. So if I was to draw a line, so you pretend like this is a ruler, I want some points above and some points below. So you can see that this one point here is really below. So if I want a couple above, I think I would go something like that. Okay, so I'm going to call that my line of best fit. So let's double check I've got all the features. I've got a title. Yes, it's describing independent and dependent variables and the situation. I have my axes labeled, I have an appropriate scale drawn, I have data plots, points plotted, and I have a line of best fit. Awesome. So the next thing that we are going to do is interpret the graph. Oh, why did all these go away? 14, 16, 18. Oh, all my things went away. 2, 4, 6, 8, 10, 2, 4, 6, 8. That was weird. Okay. Just going to save that before it goes away again. Now we're going to calculate the slope. So again, we can only use a data point if we go through it perfectly. Otherwise, you're going to be looking for somewhere that your line of best fit goes perfectly through an axis. Okay. Now, when I look at my data, actually, the way that I've drawn my line of best fit, I'd say that this data point would be great to use, or this point here goes through my axes as well. So I would say actually either of those are fine, but the last one, it didn't go through any data point, so I couldn't use a data point. And I can't say that enough. If you don't go through a data point, you cannot use a data point. But for this one, I actually will. Which one do you think is better? I'm going to say this one is actually the best. So I'm going to say that 11.8 is what I'm going to use to calculate the slope of a line. So again, it's rise over run. So I'm going to rise 8. And I'm going to run 11, or y2 minus 0 over y1, or x2 minus 0. What is that going to give me? So 8 divided by 11. Now this is where I always get really confused about sig figs. Even myself, I will not say I'm perfect with this. My original speed had all 2 sig figs, but then my distances all had 2, except for this 8 had only 1 sig fig. So I don't take marks off. It's kind of a judgment call at this point. I think if you're actually doing data, there'd be some more things in there to let you know what to do. I'm going to call it 2 sig figs. So I'm going to say 8 divided by 11 is 0.73. But if you put just 0.7, total judgment call, right? It's not that I don't care. It's that I'm not 100% sure what would be perfect. So if you put 0.7 or 0.73, I'm okay. I'm really looking that you know how to calculate a slope using a point that your line goes through, more than the sig figs. So what does the slope represent? Well, the slope represents the change in stopping distance. Stopping distance over speed. Now, that one, when you go to units, is a bit trickier. So it's stopping distance over speed, which if anybody's super mathy, you might know that it's actually time. It's actually the slope of this line is the time it takes to stop, but you're not expected to know that. So as long as you have something along the lines of the change in stopping distance over speed or meters per meter per second, I'm okay with that. If you're mathy and understand that the slope would represent the time it takes to stop, awesome. But you're not expected to at this level. So what is the equation of this line with appropriate variables? Well, it's always y equals kx or y equals mx. The y value is stopping distance. The k is that 0.73, 0.7, and the x is original speed. So if you want to use an s, that's okay. I find my s's look like 5, so I'm going to put v for speed because that's what physics uses for speed. But you can use whatever you want there. I just don't want you using y and x because I want you to understand that you can then put in speeds to figure out stopping distance or vice versa. Now, this question is worded a little bit differently than the other ones. It says, did the experiment verify their prediction? Explain. This is getting you ready for the lab. So let's pretend that the objective of this lab is to determine if there's a linear relationship between original speed and stopping distance. And because we came out with a pretty great line, we'd say, let me just change to typing. Yes, there is a direct linear, actually we can just say linear, they didn't care direct. It is direct, but a linear relationship between stopping distance and original speed at a rate of, and this is where you could put 0.73 meters per meter per second of speed. So what that means is that you need 0.73 meters for every meter per second change of your original speed. Hopefully that makes sense. Or it would take 0.73 seconds to stop for every, anyway, whatever, it's fine. So something along these lines. But what you'll notice is that I've been trying to train you, if you're given a question like, did the experiment verify their prediction? Was there a linear relationship? It's describing it in words. Yes, there's a linear relationship between stopping distance and original speed at a rate of 0.73 meters per meter per second of speed. Okay. Actually, let's put that in there. Meters per meter per second of speed. Awesome. Okay, so the next thing we're going to do is we are going to draw this graph using a computer. And I think what I'm going to do is make another video so that if you just need to watch that when you're doing your lab, you can.